Welcome to the 16th lecture. In the last lecture, we proved Kleitman's inequality. Today, we will see a couple of applications of the inequality as well as see some generalizations. In fact, today we will only see one generalization. The rest of the generalization we will see in the next lecture. Okay. So, let me recall the Kleitman's theorem, which we stated and proved in the last class. If script A and script B are two downsets of n, so they are subsets of there are a collection of, not subsets, there are a collection of subsets of n or a subset of the power set of n, such that if a set is in the collection, then every subset of that set is also in the collection. That was a definition of downsets. I'm sure you will remember it because we worked out a lot of examples in the last class. And the conclusion of the theorem is that A intersection B is lower bounded by cardinality of A times cardinality of B times 2 power minus n. Okay, don't forget this 2 power minus n sitting here, but you can take this 2 power n to the other side and also introduce one more 2 power n on both sides in the denominator to interpret this inequality as a inequality on probabilities, right? So equivalently, Kleitman's theorem can also be remembered and stated this way: if you pick a subset of n uniformly at random. Okay. By the way, remember that you can do this in two ways. One is you assign a probability of 1 by 2 power n for each subset and then pick one according to that distribution. That will be the default way to pick a subset of n uniformly at random. Alternatively, you can toss a fair coin at each element, so you can do this n independent coin tosses and include those elements for which the coin lands a head. It will turn out that this will also produce this is also equivalent to picking a subset of n uniformly at random. Okay, so for either of these experiments, Kleitman's theorem tells you that probability of A intersection B is greater than or equal to probability of A times probability of B, provided A and B are downsets or monotonically decreasing events. So in the terminology of probability, we say that these two events are positively correlated or positively dependent. One happening can only improve the chances of the other happening, never decrease. Okay, that's what if you now rewrite this in terms of conditional probability, you will see that probability of A given B is greater than or equal to probability of A. If you divide everything with probability of B, that's what you get. Or if you divide with probability of A, then you will say that the conditional probability can only improve. Okay, it will never go down. Okay, I'm kind of not emphasizing on whether it's a strict inequality or a greater than or equal to. That I think you're okay with that, right? And corollary. Now, this was about Kleitman's theorem. We insisted that both A and B are downsets, but we get two easy corollaries, by just some algebraic manipulation. Again, it's the same probability space. It's uniform on the power set of n, which means you are picking a subset of n uniformly at random. For that probability space, P of A times, oh, this was wrong. I should have written P of A intersection P of B is greater than or equal to PA, PB if both A and B are downsets. But a similar thing is easy to prove either directly or by just doing some manipulations, that if both of them are upsets, upward closed, then also the same inequality holds, while if one of them is a downward closed and the other is upward closed, let's say A is a downset or B is an upset or vice versa, A is a upset and B is a downset, in both those cases this inequality reverses. Okay, so note that here the inequality reverses, right? I'll just pick one of them and show how we prove these things. Assuming Kleitman's theorem. So if A is a downset and B is an upset, okay, so this is one condition here, right? But then if B is an upset, the only observation we need is that B bar is a downset, which we saw very clearly in the last class, right? This is the complement of the family. This is not the complement in which you go inside of the family and complement every set. No, this is not that. This is taking just the complement of the family. In which case, what is P of A intersection B complement? This is equivalent to P of A minus P of A intersection B. Okay, now this A and Oh, okay. I think I should have written P of A intersection B is P of A, P of A minus P of A intersection B bar, and hence this is by Kleitman's inequality, the version we already know, A and B bar are both downsets, okay, not B, A and B bar are both downsets. So the equality applies with a greater than or equal to, but because of the minus sign, because of this minus sign here, we get a less than or equal to here, okay. And then P of A, if you pull out, you will get 1 minus P of B bar, which is nothing but P of B. That's it, right? Easy proof. Okay. Once, I won't claim that the Kleitman's theorem's proof is easy. I'm saying once you have one version of it for two downsets, now proving any of the three other cases in this corollary is straightforward. Okay. With that, let's move on to some very quick applications. It's a very easy application. The only it's only conceptually difficult because of what is the objects that we are studying. Application of the Kleitman's lemma is going to be very easy here. So let P, the script P, denote the set of all n-vertex planar graphs. Now remember, we have already seen that this is a downset, right? Why? Because if you take an n-vertex planar graph and remove an edge, it still remains planar. So our subset relation here is essentially a subgraph relation, because your graph is modeled as a set of edges, and hence a subset of that would mean another graph which you obtain by removing certain edges, 0 or more edges from the original set. Okay, and script H denotes a set of all n-vertex Hamiltonian graphs. Okay, graphs which have a Hamiltonian cycle in them. This is not a downset, this is an upset, because once you have a Hamiltonian graph, deleting an edge may destroy the property of being Hamiltonian, but adding an edge will never destroy the property of being Hamiltonian. Okay, and now the only other thing that I want you to pay attention is what is the size of the domain. Okay, the domain is the power set of something. What is the size of that something? That is not n, but it is n choose 2, because we should think of these as subsets of edges of Kn. Okay, we have n vertex graphs, so the set of all possible edges, you have n choose 2 of them, the edge set of Kn, and this any planar graph you should think of as a subset of Kn, or a subgraph of Kn, or a subset of the edges of Kn. Okay, so yeah, make sure that you understand why we have a 2 power n choose 2 and not a 2 power n. Okay, so once you understand these things, the proof is just a direct application of Kleitman's corollary, maybe this time, one of the second lines here. Okay, we only have to argue that both P and H are subsets. No, P and H are not subsets, sorry, they are subfamilies, right? They are collections of subsets. Each graph is a subset. They are collections of graphs which are all subgraphs of Kn. One is a downset, the other is an upset, and hence you can use Kleitman's corollary almost directly, right? No calculation, nothing. Okay, but this is about cardinalities. It's about the number of planar graphs on n vertices. You should read this P intersection S as the number of planar Hamiltonian graphs on n vertices. We are saying that number times 2 to the power n choose 2 is upper bounded by the product of the number of, or it's upper bounded by number of planar n vertex graphs times number of Hamiltonian n vertex graphs. So this is about cardinalities. Now we will revisit this application, but this time we will talk in terms of probabilities rather than cardinalities. Okay, it's only at this level it's only a matter of terminology, but but immediately we will see that talking in terms of probability helps you generalize. Okay, so this is a graph. This is a way to construct a graph randomly. We have done this many times. What we do is, you consider n vertices. This is nothing new, but I thought one time we should maybe state it a bit more rigorously. We take some n vertices, and each of the n choose 2 edges you decide to include in your graph by tossing a fair coin. Okay, this is a random experiment, and the outcome, the sample space of this random experiment consists of n vertex graphs. Okay, so the empty graph is one possible outcome. If all your 10 coins, all your n choose 2 coins turned up tail, for example. The complete graph itself is a possible outcome that happens when all the coins turned head, but most of the time you will get something in between. Generally, you will expect your graph to contain half of n choose 2 edges, right? Because it's a linearity of expectation argument. Each edge is there with a probability half. By the way, this is also equivalent to uniformly coloring the edges of the graph with independently and uniformly coloring the edges of a graph with red and blue and only retaining the red edges. It's a same thing. It also turns out that, which is more important, it turns out that you can actually take all the, how many graphs are there on n vertices? You have 2 raised to n choose 2 graphs. Okay, we are talking about labeled graphs. Okay, so something like something like 1, 2, 3 is considered as a different graph. Is considered as a different graph from 2, 1, 3. Okay, so we are only talking about labeled graphs. So there are 2 raised to n choose 2 graphs, because n choose 2 edges, either each edge can be either in your graph or not in the graph. So 2 choices per edges, right? Now if you take all these 2 raised to n choose 2 graphs, arrange it, put it in some bucket and pick one of them uniformly at random, you get the same distribution. Okay, you can actually, maybe I have calculated it somewhere, but it's easy to calculate, right? You take any graph G, what is the probability that by doing this experiment, by tossing a coin at each edge, you arrive at G? This will happen that for each edge, let's say G has m edges, then m edges, then for each edge, each edge in the graph, the coin should have landed a head, which will be half power m, and for each edge not in your collection, you should have landed tail. Okay, n choose 2 minus m times the coin should have landed tail. There is independence among the coin tosses, so I am right in taking the power and multiplying. But since it is half in both cases, this always turns out to be half to the power n choose 2, which is exactly the uniform distribution. Which means when you are saying you pick a graph according to this random experiment, you are essentially giving the same probability of picking any of the 2 to the n choose 2 graphs. It's a uniform distribution. Okay, we will generalize this to GNP later on, where the probability is not half but some number p between 0 and 1. And now this P, the planar graphs, we can model it, or you can think of it as the event that G is planar. Okay. Now here the only thing I want you to realize is that these are the same objects that we are referring to. In the earlier case, P was a collection of. In this case, P was the collection of planar graphs. Oh, sorry. In this case, P was the set of all n vertex planar graphs. Here we are calling the same P as an event. But I want you to realize that both of them are the same thing. Calling them as the set of planar graphs or calling them as an event is the same, because here our outcome or sample space is a collection of graphs. So your events are going to be families of graphs. For example, planar graphs. For another example, Hamiltonian graphs. Okay, so P and H happens to be events, and the downset property implies that they are monotonically down events. And what is the probability of the event P? That's a number of planar graphs divided by the total number of graphs. Okay, and the total number of graphs is 2 to the power n choose 2. We have seen that. Similarly, the probability of the event of HB of the graph being Hamiltonian is number of Hamiltonian graphs divided by total number of graphs. Similarly, the probability of planar Hamiltonian is also similarly defined. And now we can directly apply the Kleitman's inequality in one of again the corollary form, where we have one downset and one upset. So this would be a greater than or equal to. Okay, and so we can interpret the same result this way also. The conditional probability is also meaningful to read. Okay, it's saying that if you are given that your graph is Hamiltonian, then the chances of it being planar are actually reduce compared to the unconditional chance of it being planar. Same thing symmetrically happens for Hamiltonian given planar. This is why we call this a negative dependence. Okay, and the way you have to remember this is that a monotone up and a monotone down event are negatively dependent in what probability space? This uniform probability space. Okay. But what about non-uniform probability spaces? Can we kind of, if you, instead of picking each graph with the same probability, if you had given different probabilities to different graphs, will it still remain the same? Or if you go back to the set model, if you, instead of picking a set uniformly at random or with probability 1 by 2 power n for each subset, if you assign different probabilities to different subsets, will the Kleitman's theorem still hold? Okay, at this full generality, it is false. Okay, you can easily construct small counter examples to see why. Okay, think about your universe being just 1 and 2. Okay, and now when I say I have to assign a non-uniform probability distribution, I have to assign a probability for picking what is now the power set of U. The power set of U, or 2 power U as we denote it, consists of 4 sets, right? Phi, the 2 singletons, and U itself. Okay, so and by non-uniform probability space, I have the freedom to assign any 4 probability values to these 4 sets, provided they sum up to 1. Okay, so I choose to give a probability of half to this guy and this guy, and a probability of 0 to the other 2 guys. Okay, this is also a valid probability assignment, not a uniform probability assignment, a very biased probability assignment. But in this case, it turns out that Kleitman's theorem is not valid. Okay, consider these 2 events, right? This A is the collection of the singleton 1 and the empty set, and B is the collection of the singleton 2 and the empty set. Both of them are easily verified to be down sets, right? If a set is there, its subset is also there. A intersection B happens to be just the empty set, but both are down sets. So if Kleitman's theorem was true, then you expect that the probability of A intersection B, it's a positive dependency that is greater than or equal to product of the probabilities. But here the probability of A intersection B is 0, while the product of probabilities, as you can easily check, this has probability half plus 0, which is half. This has also probability half plus 0, which is half. So the product of probabilities is 1/4. So yeah, in the full generality of the probability space, Kleitman's theorem is not valid. It's only for but this does not mean this will work only for uniform spaces. Okay, and these generalizations essentially try to extend this result to certain very large and useful classes of non-uniform probability spaces. Okay, and one of them is we can define it on general subsets, but I'll just define it on graphs itself. Okay, so now the script G and P is, you can either think of it as a random experiment, or it's also correct to think of it as a graph valued random variable. Okay, usually our random variables are real valued, but you can also think of it as a graph valued random variable if you wish. Okay, but you don't make a mistake even if you assume this as a random experiment. What's the details of this random experiment? G and P is a way to randomly to generate a graph. You go to each. It's again a graph on n vertices. The n here denotes the number of vertices in the graph. And you go to each of the possible n choose 2 edges, and toss an independent coin. The difference is that it's not necessarily a fair coin, but it's a coin which has probability P of landing heads. Okay, but remember that G and P is not a single graph, it's a random process from which the sample space consists of all graphs. Okay, here also, unless your P equal to 0 or P equal to 1, it is still, it can potentially, at least the sample space contains all the graphs. But let us say P is very close to 0, much smaller than half, then this probability distribution, or in the sample space, the sparser graphs with less number of edges will have much larger weight compared to graphs with very large number of edges. Okay, in fact, in this space, what is the probability of a particular graph, obtaining a particular graph G? This turns out to be P to the power m and 1 minus P to the power n choose 2 minus m, where m is the number of edges in that graph. Okay, so if your P is very, very small, then graphs with very large number of edges, because P power m will be vanishingly small. Okay, so small P's put very small probabilities on large or dense graphs, and vice versa. Okay, So as I told you, don't think of this as a single graph, but it's a random process which generates graph, and this is a graph valued random variable. And also, yeah, this is what actually what I had just above written. I had written it already clearly, right? The probability of generating a particular graph H, that this G is some particular graph H, is equal to this expression where M is the number of edges in that particular graph. And note that this is not a uniform distribution, right? Large P more than half would put bias towards dense graphs. P less than half will put a bias towards sparse graphs. It's uniform only when P is exactly half. Okay. Now, what is the question? Is Kleitman's theorem valid in this graph? In particular, if you think about planar and Hamiltonian graphs, even in this case, does the probability of a graph being planar, given that it is Hamiltonian, still decrease compared to the unconditional probability that it is planar? Okay. And here the answer turns out to be yes, and it's via a generalization of Kleitman's theorem. Okay. Now, I'm not really sure whether I should do the proof in its full detail, but I'll run through it, okay, and also put this as an exercise or in a tutorial so that you can fill in the details. Okay, I have written the proof in full, but there is a lot of places where it's a repeat of the proof of this uniform case which we did in the last class. Okay, but yeah, but let's really concentrate on what the theorem itself says. So now again we are back to sets rather than graphs. So let script A and script B downsets of n. But now instead of choosing a set uniformly at random, a subset of n uniformly at random, we can choose different probabilities even. Okay, in the GNP model, all these PIs are the same P, just that it may not be half. But we'll go one more step. We'll do one more step of generalization, and we allow the coin that you toss for each edge in that case or each element in this case to have a different probability of landing heads. Okay, P1 for element 1, P2 for element 2, and so on. So this is called a probability vector. Okay, and what is how do we, and this S, any subset of n is picked by how do we pick a set? By including each I into your set with a probability Pi, okay, with a probability Pi, and it is independent. Okay, but by the way, in many of the proofs I will sometimes make a error and think of this all P1 Pn to be equal to some P. The proof does not change. Okay, this almost comes for free. If you can do this for P comma P comma P, the same proof will extend for this case, and since it comes for free, that's why we state it in this generality. Okay, but you should also just for a go back to this result, that this is not, Kleitman's theorem is not true for an arbitrary non-uniform distribution, but still this is quite a non-uniform distribution, but it still holds for this distribution. Okay, what do I mean by this holds? The P of A intersection B will be lower bounded by P of A and P of B. Okay, so you have a positive dependence for two downsets. Similarly, you will have a positive dependence for two upsets, negative dependence if one is a downset and one is an upset. Okay. Now proof is again very similar to what we did in the last class. So this is many of this would just be a recap. The basic strategy is induction on n. When n is 0, your domain is the empty set, right? And you have only two possible candidates for downsets. One is the empty collection and the other is the collection which includes the empty set. Okay. Now if either A or B is the empty collection, then the right hand side is 0 because it's 0 times something, right? So yeah, and you are done. Whereas if either of one of them at least, not the remaining case is not one of them. The remaining case is only when both of them are equal to D2, in which case your A intersection B is also equal to D1, right? And now you don't even need to check what is the probability of each of these sets. Remember, it's a bit difficult to say, right? But you need not check that. In fact, actually you should check that, right? Why do I say that the probability of D1 is 0? Because it's an axiom of probability that the empty set should have probability 0. And why do I say that probability of D2 is 1? That's also an axiom of probability. The universal set should have a probability 1. So here we really do not make use of this particular model by which we pick the set, and it does not really make sense because there is no element in the set. Okay. Yeah, I understand that this is quite an extreme base case. Maybe you can convince yourself by taking the base case of n equal to 1. I haven't done that, so I leave it to you also, right? Yeah, it may surprisingly turn out to be difficult. I do not know. Exercise you can do for n equal to 1. Okay, but now let's straight away assume 0 is our base case and go to an induction step where you assume n is greater than or equal to 1. Now the same trick that we did, both the families A and B, we will partition it into A n prime and A n. Depending on into A n prime, you will add all the sets which do not contain n. Into A n, we will add all the sets in A which contain n. And we will massage this A n by now zooming in on each set in the collection and removing n out of it. That's the A n prime. The first two claims are same as what we had. A is actually this A n bar and A n is a partition of A, and hence the probability of A will be the sum of the probabilities of A n bar and A n. This is the same claim we had last day, but we did not maybe write it in this fashion. And we also know that A n as well as A n prime, not A n, are both down sets. Okay. But now the next three properties which I have colored in red are new. It was not there in last time. Okay. In fact, maybe this is the main key ingredient or the key change from last time. What is probability of, okay, now you see suddenly I have started introducing a subscript for probability. That is because I am trying from this point onwards, I will be considering two random experiments at the same time. Okay, one random experiment is picking a subset of n according to this probability vector p1 to pn, and the second, this is experiment 1, and the experiment 2 is picking a subset of n minus 1 according to the probability vector, the truncated probability vector p1 to pn minus 1. Okay, and since sometimes to avoid this clutter, I will denote this pn to be p, so that when I write, I have one subscript less to write. Okay, this is only a notation, but this is more important. Okay, you are considering two experiments, and when you are considering two random experiments, the probabilities associated with the same event may be different. That is why I use pn and pn minus 1. There is a subscript to the probability itself to make that difference. Okay, so claim 3 says that in this first experiment, when the probability of getting this p of a n bar, okay, is equal to, now remember all these sets in a n bar are present in the sample space of the second experiment also, because you do not have n in any of these sets, so they are valid points in the sample space here also, but the probability is slightly different. Okay, because in the first experiment, apart from getting all these elements, pick any particular subset of this a n bar, maybe this is equal to, this s is equal to some s1, s2, s3, right? So what will be the probability of getting this particular s, or let me say this is some I, j, k, then it would be pi, pj, pk, and then 1 minus product of some L not equal to ijk 1 minus PL. But IL not equal to ijk where? In all the remaining elements of 1 to n. Okay, so this is n minus ijk, all of them has to get 1 minus PL. Whereas when I am talking about the second random experiment, from this product one term disappears, 1 minus Pn disappears. So now in order to write this equality, I have to introduce that 1 minus Pn back. Okay, now talking more about this is not the best way to understand. If you are confused here, pause and think about these two random experiments. Pick any particular set which does not contain n and see what is the probability of getting that set in the first experiment, and then see what is the probability for the second experiment, and then you will realize that this equality is true. We have critically used the fact that none of the events here contain S. contain the element n, okay, that we have made use of critically. Very similar argument we can do for an also. Now remember, but when you go to an, you cannot talk about an in the second experiment, because sometimes you will get invalid points in its sample space. But you can talk about an prime in the second experiment also, and you will see that Pn of an, which is can be compared with Pn minus 1 of an prime. Okay, so but here you are comparing S. Here you are comparing S in experiment 1 with S minus n in experiment 2. Okay, so that is why you get a P here and not a 1 minus P. This also the same thing I said earlier applies. Okay, you should rather pause and verify that this is true rather than me speaking more things will not really help here. Okay, now in the earlier case, we had a comparison between sizes of an bar and an prime, right? But here instead of comparing the sizes, we are comparing probabilities, but we are comparing probabilities on experiment 2. Okay, we are comparing probabilities on experiment 2. But here again, but even though that adds a layer of complexity to it, proving this is actually easier than proving claims 3 and 4. Why? Because an bar and an prime still, this is something which we verified in the last lecture also. Okay, an bar is a superset of an prime. Why? Because if something is in an prime, that means if this is something which we have already verified, if S is in an prime, that means S union n is in an without the prime by definition of an prime, and that would mean S is in an bar by downset property. Okay, because S is a subset of S union n. Okay, so this an prime is contained in an prime. Both of them are subsets, even though here the subscript is n. Remember that none of them actually contain n. So they are valid events in the second experiment, and since one event is contained in the other, this inequality is easy to verify. Okay, so these are the 5 claims for this. Similarly, we can make the claims for the B also after partitioning it into Bn bar and Bn, and then massaging Bn to get a B prime n. Okay, and now we have to show that this probability of A intersection B is at most probability of A times probability B. That's our goal. The steps are very similar, but there are more algebraic manipulations than before. I may not describe all of them in detail, because again the best way to understand this is to go back to your proof for the uniform case, come to this point. These claims, proving them it's difficult but still doable, but coming up with these claims is in some sense the most interesting part of this proof. Okay, so now that we have already come up with these claims, you can try to use them and complete the proof that we want. Okay, so here again this idea is same. A intersection B can be partitioned this way. In fact, I can even put a disjoint union here. It can be partitioned this way because there is no crosstalk between a barred guy and unbarred and a tilde guy, right? And this is, since it's a disjoint union, it becomes a plus. But now earlier, now I am kind of, this change of color is a warning for you. It is to indicate that suddenly you have a change in probability. Okay, so this PR, if without any subscript, you should think of it as the n case. Okay, and suddenly I am moving from the first experiment to the second experiment, and these 1 minus P and P comes essentially from claims 2 and claims 4. Sorry, claim 3 and claim 4. Okay, so that's where this 1 minus P and P comes in. I will also kind of make a mistake if I try to reason it out. So it's better to refer back to the claim. Okay, but now in this lower experiment, the second experiment, I have my induction hypothesis. Okay, so since an bar and bn bar are both downsets and events in the downwardly closed events in the second experiment, I use in the Kleitman's lemma or the induction hypothesis and lower bound them with the product of the probabilities. I do that here as well as here. Okay, then so this red area, I am in the second experiment. Now I again use claim 3 and claim 4 to go back to the first experiment, and that is what we will get in the blue line, right? So there is a 1 minus, so, but here remember there was only 2 events here, whereas here now, because you have split 1 into a product of 2, you have 4 events. So this 1 minus p comes, but this time in the denominator because we are going in the opposite direction, twice here and twice there. Okay, so 4 times, and if you do a careful re-evaluation, this is what you get. Okay, now from this point you still have to do that clever part, which we did by drawing a square and so on, right? That clever part is still left, but you have to be cleverer. Okay, earlier you kind of said you kind of split it based on midpoint plus epsilon 1 and midpoint minus epsilon 1. Here the best point to split it is not the midpoint, right? If you actually do the computation, you will see that the best place to do a split happens to be this 1 minus p times a plus epsilon versus pa plus epsilon. Even if you add both of them, you will again get back a. Okay, but I'm thinking whether I should go into the details of this, but because there is nothing much to say. Okay, we have used of this. This is the first part of the claim that PAN bar and PN actually adds to A. But then what do? I again go back to this. Red indicates that I am going down to experiment 2. But then you don't have AN, so you'll have to talk about AN prime. But you go down with this 1 minus p factor for this, and then use the inequality there, and you can actually conclude that p n bar is is greater than or equal to this quantity. And similarly, if you do there is this. I know I'm kind of I'm not doing this properly enough, but I think it's okay. Okay, there is a p n a n bar which comes up. Okay, I'm getting. I don't find it interesting at all to talk about manipulation. But the key point is that the split point is no more the half of a. Okay, earlier it was actually a by 2, but it is p of a. Okay, and it's p of a. But again, it won't be p of a plus epsilon and p of a minus epsilon. It would be p of a plus epsilon and 1 minus p of a minus epsilon. Okay, so go through this derivation ideally by yourself rather than looking at this. Similarly, for b also we do the same. We split it at pb and 1 minus pb. But the point finally we get is that both these terms would be of the plus type and both these terms would be of the negative type. Okay, so this expression boils down to, both the pluses get multiplied together and both the minuses get multiplied together, and then things will cancel out in the way we want, and you will get that this can be lower bounded by AB. Okay, that's the rest of the proof. Okay. So that proves the non-uniform, at least one non-uniform generalization of Kleitman's theorem. You need not pick your subsets uniformly at random. You can toss a different probability coin at each point to pick the subset, provided all the tosses are independent. Okay, so now let's quickly wind up by seeing or just collecting the applications. We really do not have to. All the work was done in proving it. The applications you can just pick by the wayside. So the probability that now your G is a random graph picked according to G and P for some P in this entire range of 0 to 1, right? Then the probability that, so here we are using P1 equal to, here we are using P1 is equal to P2 is equal to Pn is equal to some P. Okay. Now, what does Kleitman's theorem say? Probability that G is planar Hamiltonian, which means it's both planar and Hamiltonian, is upper bounded by the product of the individual probabilities. So, being planar given Hamiltonian is less than or equal to unconditionally being planar, because both are downsets. But let's say connected Hamiltonian, okay, connected and Hamiltonian, both are upsets, and hence the probability of G being connected Hamiltonian is in fact greater than or equal to the probability that it is connected times the probability that it is Hamiltonian. Probability that G is planar and four-colorable. Okay. Now, planar is a downset, four-colorability is also a downset. Okay, so again it's a greater than or equal to, but why did I put it? We know that if once it is planar, then it is surely four-colorable by the most famous theorem in graph theory, right? So now if you put this in the conditional way, this is probability of, let's say one way to put it in a conditional fashion is to talk about probability of G being four-colorable given that it is planar. So we know that that probability is 1, okay, and this inequality does not violate it because this probability of G is planar times, like on the other side you will get, it will be lower bounded by the conditional by the unconditional probability that G is four-colorable, which is right. 1 is greater than or equal to any probability, but you know, none of these curious things go wrong. Okay. Now another, I don't know how useful this application is, but you know, just to see that we were only talking about 2 events, but we can actually talk about 3 events or you know, many such events, right? So think about again your graph G being sampled according to this distribution G of n comma p, and we are analyzing the probability that G is triangle free. Okay, now it looks like there is only one event, you know, where are our 2 events? You know that being triangle free is actually a down set, right? If a graph is triangle free, any subgraph of it is also a triangle free, so it's down closed, but you only have one event. So, but now I can, instead of this one event, I can think of in fact n choose 3 events. For each potential triangle, you know, for each potential triangle ijk, I can actually talk about the event that this G is ijk triangle free. Okay, so every graph which does not contain this particular triangle is in your class, and you can verify that each of those events is down closed, because if a graph does not contain this particular triangle ijk, none of its subgraphs will also contain that. Okay, so I have decomposed this, or I have split this into n choose 3 events. All of them are downward closed. Okay, so all of them are down sets. Okay, now I can apply this the non-uniform Kleitman's lemma multiple times to lower bound the probability of our event, that it's triangle free, which is the intersection of all these events, right? The entire graph is triangle free if it is this triangle free and that triangle free and the other triangle free and so on. So it's an intersection. It is lower bounded by the product of the probabilities. Okay, now each of this probability is very easy to calculate. It is just 1 minus p cube. P cube is the probability of finding this triangle, 1 minus p cube is the probability of not finding it. So that to the power n choose 3 will provide a lower bound for this. Okay, I mean, this is if these events were independent, and they are not. If these were independent, this would have been an equality. So without independence, without doing these last 2 lectures, we would have been at loss as to say whether the equality can be replaced with a greater than or equal to or a less than or equal to. But now that we know about all these correlation equalities, we can confidently put a greater than equality for this very simple expression. Okay, now, this is just an approximation for the sake. Okay, so we'll end this lecture here. In the next lecture, we will see far-fetching generalizations of this. There is an interesting history of this, and many of them did not actually originate inside of combinatorics or even probability theory. It's people from statistical physics who actually who invented some of these variations. At least the Harris's version, the FKG inequality and all were invented by physicists. And the ultimate generalization is this Alswede and Dakin's 4 functions theorem. So the only proof that we will see will be for the 4 functions theorem. Others, including our Kleitman's lemma, we can actually derive from the 4 functions theorem. Okay, we need a bit more of build up for that, because instead of there are 2 major changes there. Instead of talking about events, we can actually talk about functions defined on this sample space. Okay, in fact, events are also functions. They are characteristic functions of the events, right? That way, so this will be a more generalization of that. And the second reason why these generalizations are a bit complicated to state is that this downset and upset looks like a very narrow cases, right? So we can replace this downset and upsets using notions known as lattices and so on. But anyway, it's not we'll need to introduce a few definitions, but you will see that they are all well motivated. Okay, but that's the topic for the next lecture. Thank you.